hello everyone, I'm glad to be with you here today. So I am Erwan Neria, and I'm presenting the work titled Real-Time Stereoscopic Image Parallel Path Tracing. So the co-authors are Markku Mäkitalo and Pekka Jääskeläinen. So we are a research group from Tampere University in Finland. So first, the motivation for why we are using path tracing. So rasterization is often used in video games, but the problem here is that it doesn't give all the global illumination effects to give this like effects of photorealism. So we want to use path tracing because we are able to reproduce all the global illumination effects, such as scattering or indirect illumination. However, the drawback of path tracing is that it's computationally expensive if we want to path trace one image on a single GPU in real time. So for that, we want to expand the computational power of a single GPU, so we want to use multiple GPUs in a single node. So what about our real-time constraint? So the goal here is to make the user not notice any lag between successive images. For that, we based our real-time constraint on the critical flicker frequency. So basically, this is just the refresh rate of your brain, like at which you update new images. So it is usually between 50 and 90 hertz. Okay, a bit of background now. So the title is Real-Time Stereoscopic Image Parallel Path Tracing. So what does mean image parallel? So in parallel rendering, there are two types of pipelines. So the first one is data parallel. So basically, if the scene is your data space, and you want to divide your data space into multiple subspaces. So here, if you have 3 GPUs, we just divide the data space into 3 subspaces, and then we assign each of those subspaces to the GPUs. Then all the GPUs will, however, render in the same image space. In the case of the image parallel pipeline, we will have the same data space for all the GPUs. However, we will subdivide the image into subimages, and we will assign each of those subimages to the GPUs. Also, I want to talk about spatial reprojection. So spatial reprojection is basically reprojecting pixels from the left view to the right view. Because we know that most of the time in the left and in the right eye, you see basically the same thing. And also this allows to reduce the computational cost when we compare it to just path tracing both views. Okay, now what about the related works? So here I just present 3 image parallel pipelines. So there is the first pipeline, which is the meta-reality lab cycles, then Taure, which will be our baseline in the experiments, and finally object-oriented VR. So in the first pipeline, they do not consider spatial reprojection. Then in the second pipeline, they consider spatial reprojection, so which is interesting in our case. So that's why this is our baseline. So the problem in the first pipeline, in pipeline 1 and 2, is that their image space or their subimages are kind of sparse. So it means that all the pixels, they don't have any contiguous position, but they are shifted by 1, 2, or 3 pixels, sometimes more, it depends. Then in the third pipeline here, the problem here is that they are using rasterization. So we are not looking for rasterization, as I said in the beginning, but to have a photorealistic rendering technique. So what about the technical challenges here? So in the related works, there are common pitfalls. So basically, all the GPUs are mainly used just for rendering. So the main GPU, which is the GPU that is connected to the display, is mainly assuming all the post-processing tasks. So it means that the other GPUs will be idle, and this is something that we want to avoid. So we want to extend spatial projection and post-processing algorithms to multiple GPUs. And we want also to adapt our render to the scene variability, because sometimes a scene can be really complex, so it's hard to render in the real-time constraints that we have. So we want to respect that as well. So our pipeline. So here, as you can see, we have like 12 stages, and we render in parallel in our pipeline that we propose. We render in parallel 9 stages, from 0 to 8. In the pipelines that I showed before, like a few slides earlier, they only render like the stage 0, 1, and 2. So we see that there is some performance gain here that we can have. For the stage 2, which is the pasteurizing stage, we decide to like subdivide the image into like a large rectangular region. So this way we maximize the data locality along the horizontal axis. So why we are doing that? Because when we will reproject pixels from the left to the right eye, like the two eyes are separated along the horizontal axis, and we know it's a fixed distance between your eyes. And so we maximize this. So we show the next slide. So first we pasterize the pixels. So then when we want to reproject the views, we will reproject them from the left to the right view. So this means that all the pixels will be reprojected from the position, their source position in the left view to their target position in the right view. The problem here is that if the target position of the source pixel is not in the same GPU, it means that the reprojection is not possible. And then in that case, the pixel will be discarded. There are also like some other situations when we cannot reproject pixels, is that when the angles between the views and the surface and some surfaces in the scene have some angle that makes the reprojection not possible, and also due to these occlusions. So it means that some pixels, at least some objects, may be visible by the left view but not by the right view. So then all the missing pixels, like the pixels that we discarded earlier, they create some holes in the image. So we just reuse pasteurizing only for those pixels. So we just fill the holes. Then the images were noisy. So now we want to apply denoiser. So here we apply the SVGF denoiser. Now we see that, okay, we have like good looking images. But for denoising, there is a problem. Maybe you did not notice it in the two pictures here, but here I just zoom in here. So you can see that we have what we call sim artifacts. So this is just a difference of contrast, and it means that with this difference of contrast, you will be able to see like a line. So the problem here is that the denoiser is denoising for each sub-images. The problem is that we have a loss of spatial information, because between two different regions that are in different GPUs, there is some information missing, because the neighboring pixels that are used in the denoising stage are in fact in another GPU. So now we'll explain a bit in detail how we manage dependencies between the stages here. So let's consider the 4 main stages, like pasteurizing, spatial reprojection, hole filling, and denoising. So the problem here is that not all the stages operate on all the views. So we need to like say to the GPUs like which ratio of pixels they need to process. So for that we use what we call workload ratio. So for GPU I, we define a workload ratio WI. And so it's a pair of workload ratio for the left and the right view. So here, as you can see, we have our task scheduling framework. So first, as I said, we pasteurize the left view. So we see here that we have the workload ratio, let's say for the edge or the arc on the top of the graph. So the first one is 0.5, so it means that we will just pasteurize 1/4 of the left view. Then if we continue on the right, we have like 0.5 for the value on the right, which means we will only like spatially reproject the pixels in the right view, so only 1/4, and so on with the whole thing. Then in the end, we have like two values just before denoising for the left and the right side. So it means that we will just denoise the two views here. Then we have a quality performance control loop. So this is used to adapt the renderer to the scene complexity, because we want to make sure that, okay, we want to sacrifice a bit of performance or quality. So if we are below or above the range, the target range that we fixed. So now the results. So here, what I want to show in that slide is the performance that we have, so per stage. So let's consider the main stages here. As I said, Taure is our baseline. And so just because we render more things in parallel, so we get the speed up factor, let's say roughly times 2.75 up to times 4.2 for the denoiser. So we see that we have a real performance here, performance gain. So now we want to measure the total time, because in the table before there was not any total rendering time. The thing here is that some stages are overlapping. So as you can see in the figure in the bottom right, there are the data transfers that are overlapping with the SVGF. So in order to calculate the rendering frequency, we just based that on the make span. So the make span is the total time it takes to render all the different animated frames. So basically, we have on average a speed up factor of times 2.25 overall for the three scenes against the baseline. Now for the quality control loop. So here, if you look at the green curve here, so first we start at 10 milliseconds. So 10 milliseconds is below our target range. So we see that, okay, we can increase the number of samples per pixel, so we will increase the quality. So we start to increase the quality, so maybe in the animation, not many things happen, then suddenly maybe the camera starts to move really fast. Progressively, we add more samples per pixel, and at some point, when we arrive at around 4 samples per pixel, so the samples are the rays per pixel. So here we see that we are able to stay constantly in the target range that we fixed. So now, what about the image quality related to especially to the sim artifacts? So we have 3 setups here. So the first setup is we have sim artifacts. The second setup is that we apply a bilateral filter on the sim artifacts to smooth the artifacts. And then we have the last setup, which is we don't have sim artifacts, but still we denoise on a single GPU. So we see here that the PSNR values are not really far from each other. This is also the same for the Combi values here. The thing for a Combi is that if you have a value really close to 0, it means that there is no annoyance in terms of contrast difference. And because the sim artifact is just a difference of contrast, it means here that the sim artifacts are not annoying. But the problem here is that maybe PSNR and Combi may not be able to capture this kind of artifacts. So we have some limitation as well in our pipeline. So first we have a GPU warp divergence during the hole filling stage, because we have irregular position of the holes in the image. Of course, for the denoiser, we have sim artifacts when we denoise in parallel on multiple GPUs. Also, the denoiser cannot adapt its output depending on the number of samples per pixel. Of course, we also improve the data locality here because compared to the Cycles version of Meta and Taure, we do not use a sparse image space, but a contiguous one. So we improve data locality, but sometimes we may have more imbalance. And finally, GBFR rasterization is just the stage that we need in order to generate the buffers that we need for spatial reprojection. And of course, it's scene dependent. So if you have really big scenes, it will take more time. Okay, so to summarize, we proposed the pipeline, a multi-GPU pipeline for stereoscopic applications, especially for VRHMDs. So we show that overall we achieved a better performance against our baseline. Also, we saw that there is no significant degradation of the images due to the SIM artifacts. Yeah, so thank you everyone. And I would like also to thank my colleagues. If you have any questions, feel free to ask.